so I'm very pleased to have to welcome our second speaker, with Victor Cartelle. I hope I pronounce your name properly, Victor. Correct me.
No problem.
Victor is an early career scientist who is now working at the Flanders Marine Institute, so also called the FLIS, which you can see with his name. He did his PhD in Vigo, in Spain, and then has been working at the University of Leeds for 2 years, I think, and is now in Belgium at the FLIS. Victor uses marine records to reconstruct sea level changes, and that's why I think it ties up really well with what we were just discussing. These changes in ice sheet volume, of course. And yeah, I'm very much looking forward to your talk. I think it's pretty exotic, so very pleased to have you here. And Victor, the floor is yours.
Thank you so much. Thank you for giving me the opportunity to share our research. And I also want to thank Marie, because she made an exceptional introduction with the methodology we also use, so I don't need to explain that. So let me share my screen. Okay, so, well, first of all, I want to say that the work I am presenting in this talk is that of many people, a large group that are included in this first slide. I have probably missed some names, and I apologize for that. Well, in my talk, I have entitled this Dynamic Coastlines. The coastline has always been really relevant for the human. From ancient times to the present, we live close to it, we depend on it, and we also see that it changes a lot. It changes in our scale. We see daily, monthly, and yearly changes. But the present coastline is just a glimpse in the geological history. It has changed a lot during the Quaternary, with the sea level rising and dropping. The coastline has been moving across the shelf. And as the coastline migrates across the shelf, all the processes and different environments associated with it are also migrating. And we have different glacial processes, terrestrial processes, coastal processes that are shaping these shelf areas, that are creating different landscapes that are preserved, buried, and submerged at this moment. So they are offshore, and there are many things that we can learn from them. They are relevant to understand archaeological finds that we have in shelf areas, also to study human migration in the past. They are relevant for energy and resources. There is a huge development of offshore wind farm in the North Sea, for example. They are key areas in that they are the transition area between the land and the sea. And well, the sediment that is coming from the land is passing through these areas to reach the deeper sea. And the processes that are taking place in the shelf areas will impact the signals that are recorded in the deep sea. They are also natural laboratories. We have a huge variety of environments that have gone through fast sea level changes, slow sea level changes, changes in the different drivers, impact from humans. And the story is there. We can use them to understand the response of the coastal environments. For example, if we want to have a long scale change response to sea level change, to try to understand what's going to happen in the future, we can have a look at these submerged landscapes. And finally, they are natural archives of the past. There is many information there, and the story that they have to tell is there for us to be read. We just need to read the information that we have there. So today I am going to show two examples, one from the North Sea, where the main goal is to understand last interglacial sea level rise using records from the offshore area of the North Sea, and another example from the Iberian Peninsula. This work in the North Sea is part of a large project, which is RISER, led by Natasha Barlow from the University of Leeds. It's work in progress, so I am going to show to what point we have got, and the exceptional group that is working now in Leeds will, in the few months, probably share more updates on the actual results of the new course we got. First of all, why the North Sea? Well, as I said, the North Sea is undergoing an energy revolution with all these wind farms being built, planned everywhere in the offshore area. But the good point of this is that to build a wind farm offshore, we need a lot of information. We need to get seismic surveys. with really high resolution and high detail. We need to get geotechnical information. Even some polling analysis have been done for the building of the wind farms. And that data is there available, and we cannot get this kind of high quality and high resolution data just with the budget of research projects, because there are a lot of millions needed for this kind of research. And the other point is related to sea level and the concept of sea level fingerprinting. When the sea level changes, it is distributed around the globe, not in an homogeneous manner, in a homogeneous way. There are many factors that are influencing the distribution of the sea, of the water across the globe, from glacial isostatic adjustment to thermal expansion. And the concept I want to talk about is the gravity effect of the ice sheets on the sea, on the water. When we have an ice sheet that is growing, which is large, it has a gravitational effect on the mass of the water. And in the area close to the ice sheet, we will have a higher local sea level, while in the areas far from the ice sheet, this is going to be lower. As we melt the ice sheet, the local sea level goes down close to the ice sheet, but it goes up in the far area. If we plot this in a map, comparing, for example, Antarctic melt and Greenland melt, this is how it looks like if we melt Antarctica. We get a drop in the sea level compared to the mean, which is the black line, close to Antarctica, and a higher increase further. If we go to Greenland, it's just the opposite pattern. Most of the records that have been used to study the last interglacial sea level rise and the last interglacial sea level are generally in low latitude areas. And with these records, it's really difficult to distinguish the different contribution on the source of the water between Antarctica and Greenland. However, if we go to the North Sea, this is quite sensitive to those, and we can use these new records compared to those in the low latitudes to try to fingerprint the source of the water. That's the main reason the main framework of the project to go and explore the North Sea. So this is the area of the North Sea. This is UK, this is the Netherlands. We are in the southern part. I have plotted here the ice sheet limit during the last glacial maximum, and this is one of the reconstructions for the ice sheet limit in the preceding glacial maximum during stage 6. So we are interested in the record between them, and that's the reason we are to the south, to avoid the LGM removing all the record from the area. And these are 2 wind farms in this area that we've been working on them. This area is also interesting because there has been a lot of work done in the onshore part of the Netherlands. This is published by some colleagues where they have mapped and studied the last interglacial Moose Estuary, the Rhine Estuary, and all the deposits that are in between. So we are just in the offshore area where we expect to find this kind of deposits. And this is the kind of data we get from the wind farms. Every single line is a high resolution seismic profile, which a spacing of 100 to 500 meters. And every point is a borehole or a CPT, which is a geotechnical measurement. So this provides us really high resolution in terms of spatial distribution to do this kind of analysis. This is how a typical profile from one of the wind farms look like. It's quite messy, but because we are inside the ice limit, we can clearly see the surface here, which is quite irregular, and that we have related to the ice bands in the area during the stage 6. This is overlaid by glaciogenic deposits, and in green, we have the younger deposits with the last interglaciation and up to the present. We have mapped the surface, and this is how it looks like once we are mapping the surface. And here we have a mapping of all the features that we have above. We have subglacial meltwater channels, we have field deposits in the area, glaciotectonic ridges and outwash fans related to the movement of the meltwater in the area. With that, we've been able to refine the limit of the ice sheet in the area, which was not so far to the south. We now know that it never reached that far. It's more in the north. But what is important here is that this provides our framework to find the last interglacial deposits. When we look at what we have above, this is how it looks like. This here is another profile, and what we have here that I have labeled as P is an acoustic anomaly. That means that we have a big change in the density of the sediment. And that usually happens For example, with peat has low density compared to the surrounding sand sediments, and then we have a big echo back in the acoustic signal. And we were looking precisely for this. We wanted to find peat related to the last interglacial, so we can use it to reconstruct the sea level rise. We also know this is peat because there are many boreholes that have been done for the wind farm development, but they go through a lot of testing for geotechnical purpose, and they are completely destroyed. This is a mess that we cannot revisit to do any reconstruction of environmental studies. So we need to revisit the places and get new cores. This is from another wind farm slightly to the south because the sediments are thicker. And in blue, we have the last interglacial unit with many acoustic anomalies, which are peat. In general, we have two levels, one at the base of the last interglacial deposits and one on the top. Using the amazing seismic data, we've been able to map the surface at the base and the surface at the top. In green, we have higher areas. In blue, we have deeper areas. And we can infer changes in the landscape in the area. And also in this area, this map is full of small channels, just carving the area. It resembles some coastal environments. So this is the distribution of the peat in both areas. It's usually found in the green areas, but also some in the deeper blue ones, but always on the sides of these channels. By analyzing the sediment between both surfaces, we've been able to more or less reconstruct the landscape to get a broad understanding. So to the south of the wind farm, this is full of sand. There is no peat. There are large bodies that we have related to the Moose Estuary during the last interglacial. There is a small estuarine channel in the north, and the area of between is quite flat, quite well laminated, and is cut by small channels. So we think this is a coastal plain. So the next step, go and get new cores. That's something that was quite difficult, to be honest. There is a lot of areas which are of interest, but the main task was trying to get the highest range possible in terms of depth of the peat deposits. So we have mapped the peat. This is the depth below present sea level of the top of the peat layer, but it's not that simple because we have to go there and drill there. And you may wonder why we are drilling in areas like this and not in this huge patch of peat. Well, working offshore is not easy. This is how the wind farm looks like if we plot all the pipes, all the cables, all the safety zones, areas for development. It's really difficult to find a single spot where we can drill safely. So that's the reason why we have those sites there, because we have to agree where we are going to drill. Luckily, we've been able to do the drilling in the middle of the pandemic. So we got the cores, but they have been stuck in Boscov in the UK for more than a year because the university was closed. But we've been able to start working on them this year in the summer. Oh, yes, sorry, last year. And we got the cores, and we've been able to confirm that the peat layers are there and that we should be able to trace the flooding during the last interglacial in a range of more or less 15 meters, from more than 50 to around 30 meters. This is how the cores look like. Here we have the peat we were targeting, and the peat itself is not the most interesting part because the peat is a terrestrial environment. What we want is what is just above the peat layers. We want to identify the kind of environments that are preserved there, if there are marsh environments, if there are intertidal environments, and with that, we should be able to get how was the sea level at that moment. But I have to say, there is a long way ahead because there is many people still working on the course to finally get the sea level reconstruction. People doing modeling, people analyzing the pollen, and people analyzing the foraminiferal. The foraminiferal remains on them. And I hope they will share some of the results in the coming months. But before moving to the next topic, there is something I want to show, especially now that Marie has shown the CT scans. And it's maybe thanks to the pandemic, we've been able to test a new equipment that is available in the British sediment core facility, which is called a Scout Scan. This is a high resolution machine to get X-ray images and pseudo 3D images. The advantage is that it's quite fast. In a minute, you get an entire core scan. And this is the detail of data that we get. This is the classical X-ray image. This is laminography enhancing all the structures in the sediment. And this is how the sediment looks like once we split the cores. There is so much information there that we can use to understand the sedimentary processes that is worth a try. So if anyone is interested, get in touch with them if you want to try, because this is exceptionally valuable both to keep as an archive and to understand the processes that are undergoing on that area. The next step is reconstructing sea level rise. An interactive analysis with the reconstructions we have done of the landscape to understand how the flooding has gone and how the sedimentary environments have responded. So now I am going to show another example in the Galician Rias, which are estuaries in the Iberian Peninsula, where I've been working during my PhD and later after finishing it with the people from the University of Vigo. We are now going to the Iberian Peninsula. This is how the coastline looks like, and we have these large estuaries in the area. They are quite interesting because they are quite deep and they record the flooding during the post-glacial, post-LGN, and during the Holocene. And we have been focusing on this one, which is the deepest one. This goes down to 90 meters, more or less, below present sea level. It has a really complex physiography, but it's interesting in the sense that it's far enough from the ice sheet to more or less follow the global sea level changes. So we can try to understand the infill. This is how a typical profile in the area looks like. We have a very erosive surface at arc base, which is related to the drop of sea level during the LGM, and then this is infilled with sediments. We were interested in the earliest phase of infill during just after the LGM, and this is full of large bodies and huge amounts of sand. This is not common in this coast because the Galician coastline is more or less dominated by waves, and everything inside the rias and inside the estuaries is mud, clay, and silt. But in the record, we have these exceptional bodies well preserved here. They are large. This is 15 meters thick, is almost a kilometer long, and they are distributed all along the axis of the ria. So we've been able to track how they have migrated in response to the sea level rise. And we've been able to get some colors and get some ages. They are really beautiful bodies, and they correspond to the highest rates of sea level rise after the LGM. They are related to the meltwater pools 1A and 1B. And thanks to these high rates of sea level rise, they are preserved there and we can study them. In addition, the distribution of environments inside the estuary has changed a lot over this time. If we reconstruct the landscape, they are similar to models of estuaries for macrotidal environments, not for mesotidal environments, as is the coast of Galicia. And they are full of sand of these bodies. Once the flooding of the ria is more or less complete, it changes completely. Everything is full of mud, low energy environments, and dominated by the waves. But we were also interested in how everything is recorded in the pollen record here. So we got many cores, we got datations, and this is an exceptional example because here we have an intertidal environment with this rhythmic lamination with sandy and clayey layers, which is more or less continuous. At least there is no changes in the sedimentary record. My colleagues have been analyzing the pollen to understand the signal, and we found something weird when comparing this ria with the rest of the records around, and that there was a delay in the expansion of oak in the Iberian Peninsula, in this area of the Iberian Peninsula, of more than 1,000 years, which is difficult to explain because in every record, in other rias, in every record in the onshore area, it happens at the same time. But in this ria was recorded 1,000 years later. And it was really difficult initially to try to explain why this was happening. However, once we've been able to reconstruct the landscape changes, and we've been able to look at different proxies in the sedimentary in the sediment, we found something quite intriguing. In the Galician coast, we can use a proxy, which is the relationship between potassium and titanium, to try to understand the source of the sediment. When we have high values of titanium, this is related to quartz, and it means that the sediment is mainly coming from the rivers. However, as the potassium increases, there is some higher abundance of feldspars, which in the Galician coast is related to the erosion of cliffs and oil deposits, which is mainly done by the sea. By analyzing the core, we clearly see that there is a big jump in the trend. When we compare both, sorry, when we compare both, this is the expansion of oak in the area, and there is a huge reworking happening just before that, which is masking the expansion of the oak in the area. So we wanted to go one step further, and this is still work in progress. But we decided, well, let's try to isolate the pollen remains from this area and try to get a radiocarbon age from the pollen remains. What we are finding is that the pollen remains of these deposits are between 4,000 and 10,000 older than the sediment. So for some reason, some packages in the area are not responding to any climate forcing or any vegetation dynamics. They seem to be responding to the sedimentary processes in the area. And now we are trying to find other spots across the areas to get more radiocarbon ages to try to understand this reworking or these changes in the sources, and try to get like a good way to understand how to distinguish this signal, and therefore not using these small pollen spots to interpret the climate, but rather the sedimentary processes. So as a final remark, I want to say that the study of some submerged landscape is always a work in progress. The more data we get, the more questions we have. But there is a huge potential in these submerged landscapes to develop new sea level indicators, and therefore moving beyond the most typical indicators that are usually used in the low latitudes. The North Sea is a great location, recording the interplay of ice, sea, and climate during the Quaternary, and there is much we can learn from them. And finally, to be able to do this kind of reconstructions, which are quite complex, a multi and interdisciplinary approach is always required. Otherwise, it's pretty difficult to tackle. And that's all. Thank you so much.
Thank you very much, Victor, for this very insightful talk. It was very broad, very interesting. New results as well, always good. So I would like to now open the floor for questions. So please do raise your hands and shoot. Everybody wants to go to lunch. We have some minutes, so please go for it. Oh, Becca, I think you, oh yeah.
Yes, hello.
I think you were slightly ahead.
Oh, that's all right. I have a quick question about, just wondering, Victor, about the dating techniques you're thinking of implementing on the North Sea records.
Well, we are trying a number of approaches now. We are trying luminescence dating. There are some samples undergoing analysis now to see if we get valuable ages. We are trying to identify tephra layers. There is one person at least that is looking at that. And we are also using the pollen zones. And in the onshore area, there are lake records, which they are not dated in absolute terms, but the duration of the pollen zones is well established. So what we are trying to do is identify the same pollen zones in the offshore area. And even if we cannot get an absolute age, we can get the difference in age between the different points, and therefore we can get the rate of sea level rise. Those are the approaches that we are using now.
That's brilliant, thank you.
Thanks.
So our second question. I'm sorry, I don't know your name because I just...
Sandra, it's Sandra. Yes, sorry about that.
No worry.
Thank you, Victor, for your nice slide talk. I know that you are not, I imagine that you are not an expert in pollen, but I have a question regarding pollen.
Yep.
Because as I mentioned before, I'm like working with the U1385 from the Iberian Peninsula, it's a marine record. And I have worked also with the D13882 that is in the mud belt of Lisbon. And we have detected the same pattern regarding the delay of the expansion of the oak forest. And we have connected that, obviously. I'm just like putting that because you are like kind of explaining with more like a regional setup and reworking, because you don't have like a kind of continuous deposit. But we, in our cores, in both cores, the D13, the U13 85, the MD 95, 2042, that is a consistent pattern in 3 different cores. That is a delay of the oak expansion following the maximum insolation at the start of the Holocene. And we connected that with the maximum insolation and some like moisture stress, because the oaks are quite demanding regarding like higher temperatures that we did have, but also like moisture availability. And because insulation was so high, maybe it was not able kind of to pick up straight away with the maximum temperature, because it was like kind of stressed with the water. But I'm just putting that because there is other cores showing the same, like 3 cores. In the mud belt, continuous deposition, marine cores, like, yeah, if you want to see, that's available.
Yeah, it's something we have to consider, because in this case, all the records in the RIAs are showing the oak peaking at the same time, with the exception of Arousa. So
yeah, but there is 3 cores. I'm not saying just one, same location. But I have to say the northern core, that's the MD03 2697, it doesn't show that. And that is consistent with your like kind of trend, but the ones like not so, that's not so far away. It's like Lisbon is just like, I don't know, 200 kilometers, not some, or 300 maximum. And 3 cores show exactly the same in different locations. Anyway, it's just like
it's something interesting. I will share with my polling colleagues, because it's something we have to consider. In this case, we have explained that because of that. And once we got the ages of the polling, that polling was not representative of that time, because there was a Pinus polling and the ages we were getting were quite old. That was the first explanation. But yes, of course, we are trying to get new cores and trying to get new data to try to compare. So I will share that with my colleagues.
But also what happens is most of the cores that are like continental ones, they are not like continuous sedimentation like records at all. And you can miss something, and maybe because of that you are missing the sea level rise, and maybe you are missing something. You need to go.
I totally agree with that, but in this case, the delay is happening in an area which is more or less continuous. There is no signal of a lack of continuity. That's the reason we wanted to explore it. Because if we move to shallower records, yes, there is discontinuities and we are missing some records. In this case, was just analyzing a single package that seems to be continuous, but it's probably not that much.
Anyway.
Can I suggest that perhaps because this is a discussion which is perhaps a bit special to this area, and it's good that you guys can get in touch and try to get further in these complicated problems. I understand. I do have another question, which is perhaps addressing both speakers, because you showed Victor, and I mean we already heard about that, the sea level changes following a deglaciation is complicated, and it's due to different mechanisms. And you showed that you would get a decrease in sea level closer to the ice sheet. And I'm wondering if you already have records showing that, or because I know it's based on modeling mostly. So do we, and so that's addressing both Victor and myself, whether you know of records who are already showing that.
I know that it's mostly based on modeling and the distribution, that there is so much work still that it needs to be done to understand that. In the case of the North Sea, what we are doing is also combining all the analysis with modeling before being able to get to any conclusion. There is a PhD student that is doing that and doing the modeling for the ice sheet in the LGN and in the previous stage, to try to get the different signals. So that's the only thing that I can say about the North Sea now. I hope once we get the rates and once we get the final data, we should be able to try to disentangle that complex question.
I can say we have not seen any indication of this. On the other hand, depending, I assume we are not talking about a huge change. No. And the question is, can this even be seen in a marine record of several hundred meters water depth, right? Because a few meters more or less doesn't make any difference.
Exactly.
So we have to go to places. I think it's not sediment cores like these. We actually have to go to the coastline to see information, if we can do that, because this is very precise information. So I don't think this is the right methodology to check.
Yeah, I do remember of some work being done in Denmark, I think, at Copenhagen University on that. Indeed, because they are also located in a place which has been probably moving the other way around, let's say. Yeah. No, but it's very interesting and also very relevant, of course, for us to understand what we are probably looking at. Any other question from the audience? Okay, seems not. Was also very impressed by your.
I have one question. Hi, thank you for a very nice talk. I think it's a question for Marit, but I don't know, maybe Victor can also answer. Did you see some kind of, when you studied like Greenland ice retreat, differences in rate of different retreat in different part of Greenland, like how in comparison to the last glacial period and maybe in the late Holocene, if the freshwater input into the North Atlantic are coming from different parts of Greenland and how this can affect, for example, the AMOC circulation or climate in general? I don't know if my question is clear.
I think you are asking whether we can see that some parts of Greenland are melting more than others over time. Is that what you asked?
Especially changes in where the freshwater input from Greenland is coming to the North Atlantic?
Well, in itself, when we look at sediment cores, for instance, around Greenland, yeah, there it's possible to see, get an idea of where the melt water, in which areas we have melt at different times. And it's clear that not everything melts at the same time. There are differences. There are also differences in general warming and so on. The ocean currents are linked, but they are not precisely all sort of happening always the same time, all the changes. So on the other hand, if you're talking about where the water sort of enters the North Atlantic, well, on the east and west Greenland side, it will come in different routes, right? On the West Greenland, the meltwater would actually go all the way up to Baffin Bay, a lot of it, and then through the subpolar gyre. In East Greenland, it would travel more directly down south along Greenland, but then it could, some of that, go north again along East Greenland, but it's already basically then in the subpolar gyre. So the routes are a bit different. Also from the north, it seems to be an even more important. But that is linked to the ocean circulation more than the actual melting itself. That's basically where the meltwater comes into the ocean.
Okay, no, my question is related because there is now a lot of discussion about the current Greenland ice melting and where this freshwater input from the current melting can affect the AMOC and in general climate, because it's apparently it's different than the melting of the Greenland ice in the early Holocene, when people can compare the both situations. But yeah, very, very good question, answer. Thank you.
So I see that Rick has a question.
Yeah, I had one last question, actually more for Victor, and it's compared to Celia, much more regional stuff. Maybe I missed it, but you show these records of different, say, detrital input, if you want, from a river or from coastal erosion. How are these processes related to sedimentation rates?
Yes, well, we have just started to study those processes there. So what we are now doing is trying to get a budget of the amounts of the volume of the sediments inside the areas and try to understand those sedimentation rates and if there is a change. Because what we think is that there is a huge recycling of sediments from one phase to the other. So what we are trying is get those erosive surface, the volume of sediments between them. We have a lot of radiocarbon ages across all the packages, and we hope to tackle that question. Doing that is just a work that I am trying to do when I have some free time from my new job, but that is going to be the approach that we want to do.
Yeah, that makes sense. All right, thanks.
Thanks for the question.
Thanks. Any other question? Okay, I have just a very short dummy question. What is an iceberg plow mark?
Well, when you have an iceberg, you know that only about 10% of the iceberg is above water, and the rest is below the water. And when the iceberg moves either with ocean currents and winds, they are pushed, and then often they will hit the seafloor and can make deep trenches of tens of meters down. And by looking at the depth, the present depth of where you can find iceberg sort of scouring, there you can get an idea of the size of the icebergs that existed.
Right. Yeah,
and we can, for instance, see that today we all know that Antarctica has these huge icebergs, right? And Greenland, we sort of normally see these nice, cute icebergs that look precisely like they're supposed to do, right? But during the last glacial period, for instance, where the ice moved all the way out to the shelf, we had icebergs that looked like Antarctic icebergs.
Okay.
But when you have plow marks or scouring from the ice, or from icebergs, they go in the direction of the ocean currents and not of the ice that moves from the coast. And that shows that you did not have sort of ice that was ground or sort of directly ice sheet ice, because you can't have icebergs and ice sheets at the same time at the same place.
Yeah. Oh wow, that's really fascinating. That's like jumping right back into time.
Last summer, we actually tried to core into one of those plow marks. We're not sure whether we managed to do that. It's, you know, drifting. The ship was drifting too fast and so on. But last night, a colleague of mine they did CT scans of the core. So we are really excited to see what's happening.
Nice.
If we succeeded.
Cool. So we caught you just a little too early.
Yeah, well, if it's plow marks, yes.
Right. Okay. So I have many more questions, but I think we should probably stop here. We are over time already by 10 minutes. So I just wanted to close the session, and thank you, Marit Solveig and Victor, a lot, heartfully again, for your very nice, very interesting talks. I mean, I learned a lot. And I guess we will see each other in June, at the end of June, for our next seminar series, and this will be more on terrestrial records. Until then, please do contact us if there's anything. We will put the recordings online on our YouTube channel, very professional. And by that, I wish everybody a very good day and see you soon.